Coming, everyone. Um, I think the first thing I should say is that I was kind of caught the tail end of the keynote, and I did not pay Mehul to tee this talk up, but it happened by coincidence pretty nicely. So um, I am the CTO at Iron Core Labs. We build tools to help software developers add privacy and security into their applications and data stores. And I was here last year for OpenSearch Con, and we had just introduced a new product called Cloaked Search, and it's built to help protect sensitive data in keyword indices like OpenSearch. We had just come out with that, and so I was here. And last year there were a few talks, maybe more than a few, about vector indices and search over those indices. And to be honest, I paid very little attention to those because I'm not keeping up on new trends, apparently. And I saw those and I was like, well, that's interesting that there's some, it's a topic. But, if you fast forward a year, some things happened in the last year. And I'm sure that you've probably heard a little buzz about some of them. And one of them that I'm sure you've heard something about is AI phenomenon of generative AI. So these new large language models like ChatGPT, right now, I guarantee there's someone sitting out there using ChatGPT to write an essay for their homework assignment. There's probably a few thousand people out there doing that. So I've been through several waves of the new AI hotness in my career, and this one feels a little different. The magnitude and the intensity of the buzz are significantly more. And I think more importantly, this one feels a lot more real. And a large part of that's because it's here right now. It's not some look into the future about what might be happening. It is happening right now. So one of the key parts of this new AI wave is you've probably heard the term vector embeddings. So all of these new AI algorithms, a lot of them produce these vectors of floating point numbers, and like a lot of other digital representations of things like pictures or audio, they don't mean much if you just look at them. But these embeddings, they somehow encompass a summarization of the input in some sense. And you can take these embeddings, you can store them in a vector database, and then you can use tools like nearest neighbor search to find similar vectors. So these kinds of search can be used for finding semantically similar text. Maybe you can find images that contain similar objects, or you can do similar preferences in a recommender system. There are a lot of related tasks that you can use these vector embeddings for. So when we think about a keyword index like OpenSearch, it's pretty easy for us to understand some of the potential problems with storing data in that, sensitive data in particular. If someone was able to get into the data store for an OpenSearch keyword index, it wouldn't be very hard for them to look through it, find terms of interest, and to go from those terms of interest to finding the documents that contain those terms. I mean, that is exactly what the index is for, after all. So, and to make it even a little bit worse, a lot of times you configure the keyword index so that it also contains the positions of the words in the document. And so if you are able to get into the index, even if somebody didn't store the whole document in the index, you can probably recreate a lot of the text just from accessing the data storage for OpenSearch. It's a lot less obvious to most of us, myself included, that there are similar risks involved when you're talking about handling the embeddings that might come out of one of these transformer models or some other AI feature extractor that spits out one of these vectors. But I'm going to try to convince you today that these embeddings need to be handled with the same care you would take for handling other sensitive data. So we'll get into that as we go through the presentation. And so I'm going to try to convince you that if you are getting serious about protecting your data, whether it's your customers or your users' sensitive data or your own internal data, that you need to pay attention to all of your data stores. And that includes your search services. That includes not just your text search service, but your vector search service. OpenSearch provides both kinds of indices, and you need to think about securing both of them. And There are a lot of reasons to do that. I hope that one of the most important reason is just because it's the right thing to do. But to further drive that point home, uh, just like winter, regulation is coming. So you can see on this slide how many states have passed or are working on passing privacy laws. And these privacy laws that are depicted here are not specific to AI data, but they talk about a big part of all of these regulations is requiring systems to be secure by design and by default. So um, regulation is coming to, it's already here in the EU. You've probably heard of GDPR. It's here in the US and it's spreading state by state. And so this is another reason why it's time, or maybe past time, to take a serious look at how you secure sensitive data. So in the talk, I'm going to give you an overview of AI. If you're already familiar with this, won't take too long, so hang in there. We'll get to some more meaty stuff after that. I'm going to give you a little bit more background on embeddings, what they are, how you can use them, and then the meaty stuff is why you need to treat them as sensitive data. And then I'll talk about a technique that we use to help you protect those embeddings if you are dealing with them, to make it harder for an attacker to extract sensitive data from them. So let's just start talking about AI. What is intelligence? What does that mean? And what does it mean for it to be artificial? There are a lot of different answers to that question. An AI algorithm is just another computer program. It takes inputs, runs some process on them, and produces outputs. It's just another mathematical task. But when we think about AI algorithms, there's something that seems different about them. And a part of that is because for a lot of the AI algorithms, it's a lot harder for us to understand what's happening inside of that box when it's doing its job. Part of that's because of the nature of the computations that it's doing. And a part of it is because the algorithm's actually broken up into two different phases. So the first phase, the algorithm is provided a bunch of input and it takes note of associations that it finds in the data. And it's kind of preloaded for what kind of association it's going to learn. But it captures those associations. And then after it's captured those, it can be used to feed new inputs to it and to produce some new ideas about what those mean. And an interesting thing to me about that is it seems very familiar to us, and I think a lot of that is because it's intended to be a lot like the way our brains work. The human brain is not a calculator. It's a pattern matcher, and it's an incredibly good pattern matcher. It knows, it's very good at classifying things and making connections between things. So the rest of the talk, I'm going to use a brain, and I think Mehul did this too, to represent this AI black box. And one of the reasons why this is a common thing to do is that a lot of the current AI algorithms are actually at least loosely based on the idea of neural nets. And the neural net was an attempt to capture the way that the brain works in an algorithm. So we've got this AI brain, and we have a training phase that I talked about where it learns these associations and it stores them as a model. And you've probably heard of these AI models, particularly now with the generative AI. Once you get through training it, you can give the model new prompts or new inputs, and it's going to produce inferences about those new inputs based on what it's been trained to do. And the interactions between the pieces of the inference engine, they're not easy to understand or to predict. And that's not really that dissimilar from our own brains. Obviously, we don't understand very much about how our own brains work, even today. So the human brain is far superior to any of these algorithms in just about every way. One way that's maybe a little more debatable is in our memories. Human memories are pretty amazing. They mix together all of our senses. And if you compare that to an AI memory is pretty shallow. The AI algorithm has a limited understanding of some pretty specific inputs that it can process and that can produce these memories from. But human memories are a little curious. They're kind of liable to be modified by ourselves or by others. We're kind of prone to getting false memories based on suggestion that we're given from other people. We don't have any direct control over the way that memories are retained by our brain. Sometimes they age out. We're not really sure when they will, but trust me, as you get older, you'll discover this more and more. They do age out for sure, um, but maybe not always. I've been to a couple of music events recently. It's like, man, I thought I'd completely forgot like this old song lyric, and bam, it comes out. But we don't have a lot of understanding or control over how those memories are floating around in there and how they get accessed and when they go away and stuff. In contrast, the AI ones, you keep them and they're there until somebody says they should be deleted, and the AI can use those whenever it needs them. When we process information, we filter it extensively, and we're quick to throw away anything that we get as input that we don't perceive as important. So if you take a look at this photo, for example, you take a quick look at it, you probably get a pretty good understanding of what that's about very quickly. Like I looked at that, I immediately was like, oh, this is a guy on a skateboard in a half pipe. He probably is doing some kind of ride. It looks like it's maybe a contest. There are some people standing around watching. I thought, well, it looked like it was probably summer. It's definitely a black and white picture. But beyond that, I would have to intentionally study it to extract more information out of that picture. And AI doesn't filter like that, like we do. If it's been trained to do so, it would immediately look at that and go, oh, I know the number of people that were in there, which just coincidentally, there were 17 people in there. It might know how many tent canopies there were there, or what the text was on the different signs that were around the edge of it. So for me, those were not important details. Maybe if I was in a different context when I looked at the picture, it would have been, some of those other details might have been more important. But the AI is trained to produce these inferences, and it's always going to do that, and they can be stored away for later use. So when we're talking about an AI system, I think it's useful to think of it in two separate pieces. So there's the model piece of the brain. That's the knowledge base, the recognition center that produces the decisions or the inferences. And this part of it represents everything that you expose the AI to during its formative years. The first phase, the training phase of its life cycle. So this part of the brain doesn't really have anything beyond that AI childhood. It learned those things, and that's what it represents. If we call the other part of the brain maybe the memory in an AI system, that's everything that you expressly want the system to retain that it's shown from later use. So, after it got out of childhood and it's out there in the world, once you've trained it, you show it new inputs, it's going to produce inferences, and you can retain the output of that inference in your memory. So this memory is what people mean when they talk about vector embeddings. It's likely, I think, that you've heard that term. And the vector embedding is just a reference for the digital format we use to store the inference that's produced by one of these models. So these AI memories, you can store them in a lot of different ways. Maybe you just store them in memory in your inference system. Maybe you write them into some sort of index files, or more recently, you might store them in a vector database. And going forward, that, I think, is going to be the predominant way that people will persist these inferences because of the capabilities that they provide. And we'll talk about that. The key takeaway that I want to give you from this talk is this. Any embedding that is produced by an AI model, you should consider that embedding essentially equivalent to the input that produced it. You can take that vector embedding and you can, in some sense, recreate the input that generated it. So an AI, if you fed an AI a document and it generated a bunch of embeddings from that, those are going to allow the AI to tell you about the document like theme by theme or section by section. It might not be able to exactly spit out the text verbatim, but it's going to be able to convey to you the meaning. It can recreate images, plots, voices, faces, or anything that it's trained to capture. So these new large language models encapsulate a lot of information in each output, and they've got a lot of understanding of their input. So you can use that understanding in a lot of ways, but it means that there's a lot of context that's captured in one embedding. So I'm going to talk about this recreation task more as we go along. So we've talked about embeddings, what they are. Next, I want to kind of talk about what you can use them for. There are a lot of different uses for embeddings. Uh, in the past, a lot of AI involved, you had a problem you wanted to solve. So you would come up with a model that you thought would work for that problem. You would train that model and then use it to try to solve the problem. It turns out that today, a lot of times, it's actually a better choice to use a more generic model that's already been trained by someone else. You let somebody else spend their millions of dollars on AWS time to train a model, and then you can use it. And if you couple it with the right memories and good prompts, you can probably get results that are as good or better. So I'm going to look at 3 use cases in particular where people are using AI, and then we'll talk about a couple other things before we move on to talking about privacy and security. One of those is facial recognition. You can train a model to pick out faces in a photograph, and then you can train the model to understand the differences between faces, like maybe the relative distance between the eyes and between the eyes and the mouth. And those are things that humans use to differentiate between people. And you could train an AI model to do that. And when they detect these faces in a model, they spit out embeddings that represent those faces. And so if you gave it a picture like this, it might spit out an embedding for each of the faces that it represented, and it can send those off to a memory. These embeddings are just vectors of numbers. So given a vector that represents a face, you can see if that is in other photos, or you can see if there are similar faces in that photo or other photos. So if we can do that because these vectors have the normal properties that you associate with vectors. If you think of one, just a 3-element vector, it's easy to think about how to represent that in a 3-dimensional space. And if you do that, it's easy for us to see which vectors are similar to each other and which ones are not. So given a vector, it would be easy for us to look and see if there are similar ones. So if there's a vector that represented a face, and if you could do that in 3 numbers, it would be pretty simple for us to see what are similar pictures that contain the same face, or maybe what are similar faces. The key idea here is that because these are representative vectors, the idea of similarity is something that's easy to compute with an algorithm, with a computer. And so you can use that to cluster images or cluster vectors, or you can do nearest neighbor search on them. And that nearest neighbor search is the core reason that vector databases exist. The primary operation that those databases do is nearest neighbor search. And you can use that for finding groups, predicting sequences, in addition to just finding similar items. So these vector databases are tuned to work really well with a lot of high-dimensional vectors, and that means that they can hold a lot of them. That means that they can hold a lot of potentially sensitive data, like images of people's faces. So the second use case I want to talk about is semantic search, and I think you've already heard a little bit about that today, and there will be more. There are a lot of different names for semantic search, but they all mean the same thing. The key idea is that you're trying to understand a query not just in terms of the words, which is kind of the traditional keyword approach, but in terms of the meaning of the search. And so if you did a keyword search in a keyword engine like Wikipedia, like say you look for Barack Obama's wife, you get back a bunch of documents. They contain the words that you asked about, but in this example, they were all articles about the former president. And that, obviously, when you look at the query, that's not what you were asking about. If you did that same query in Coggy or Google, a search engine that has a semantic engine built into it, the intent will lead you to a lot better results from the query. Another place that this can be useful is when you're searching for words that have a lot of synonyms, like consider arms. You could be talking about elements of a group, like the political arm of an organization, or bodily appendage. You could talk about arming yourself with knowledge, calls to arms. You could talk about strong arming people. And those are pretty significantly different ideas, but they're all the same word. And a lot of search engines don't understand that difference. They just understand that the words are equivalent. So with semantic search, you can understand the meaning, and you can get, if you searched for building strong arms, you might get weightlifting documents. And if you searched for strong arming somebody, maybe you'd get maybe you'd get a document about mafia pressure tactics. There are a lot of ways to implement semantic search. Ontologies were a pretty popular way for a long time. But with the new large language models like SBERT or Ada, the OpenAI models, you can do some pretty amazing things to implement semantic search. If you take a document, you break it up into chunks, and maybe for each chunk, you add a little bit of the preceding one, a little bit of the following one, so you can kind of produce some context that ties them together. You take each of those chunks, pass it through one of these AI models, and you ask it to summarize what it saw. It will spit out an embedding that represents that summary. You can send those off to a vector database. And then when you get a query, you do the same thing. Run it through the model, get a vector that represents the meaning of that query. You do a nearest neighbor search in your vector database, and when you get that back, you find chunks of documents that most closely match the query. You can retrieve those documents, or you could use a generative AI to take that embedding and summarize the document for you. So OpenSearch gives you the tools to do both of these things. You can do a keyword index search. You can do a semantic search. Combine those results together to get a lot more relevant responses. The third use case that I want to talk about is anti-hallucination. I think that Mehul was talking a little bit about that too. This is in the context of the chatbots, the generative AI bots. Maybe you're asking it questions and it comes back with answers, and it's absolutely convinced about those answers. And the problem is that it's trained to produce plausible responses, meaning they're probabilistically likely, but they're not necessarily true. They're not accurate necessarily. To prove this point, we asked several of the open source models, what is Iron Core Labs? And all of them guessed that we were a tech company, but none of them knew what we did. We're a cybersecurity company that has a data protection platform, and they guessed a lot of other things, including blockchain, which made me cringe because I'm just not a big blockchain person. So, but all of those answers, it was absolutely convinced those were right. And it generated a lot of text to go along with it because it is, after all, a generative AI. And so this is a pretty benign example, but you can imagine that it could be a lot worse. So how do you get those responses to be more truthful? A way that's gaining traction today is to provide context when you ask the question, and then the algorithm can strain out some of the possible answers that don't fit with the context. And that process is often called a retrieval augmented generation workflow, or RAG workflow. And it uses these embeddings often to find context to feed into the model. Chatbots can remember the embeddings from the questions that it was asked as sort of a context for how you got to that point in the conversation. And then you can use semantic search, say, to go find items in a vector database. So maybe if we had processed our website and put the embeddings from that into a vector database that we could use to search and provide context, we could have gotten a lot better answers about what is Iron Core Labs. You just take the question, you do the semantic search, you get those responses back, you can extract the context and feed it into your search engine. So this is quickly becoming one of the most common use cases for embeddings. It's not the only one. You can use these new machine learning techniques for zero-shot recommendation and prediction systems and a lot of other uses. You can use them on things that aren't text, that aren't images. So there are a lot of different ways that you can use embeddings. So now we've talked about that. Let's talk about how you can misuse or abuse embeddings. If a hacker got hold of the AI memory from a system, if they got into your other data stores, maybe they might have to sift through a huge SQL database or a lot of files, and they're grepping around trying to find things that are interesting. Well, in the vector database, if they knew the model, they could generate a vector for something that they wanted to look for and just do nearest neighbor searches and see if that was in there. So then they maybe could summarize that, and it might be a quick way for somebody to really extract a lot of data from this vector database. Now, there are still a lot of people that are not convinced that this is really a realistic attack model and that this is a risk. I'm here to convince you that I can say with absolute certainty that yes, this is something that you need to pay attention to. You need to be concerned about the sensitivity of these vectors. We've found several recently published academic papers that talk about this very thing. They typically talk about them as embedding inversion attacks. And we found a paper that was published in 2020 that claimed that for one of the popular sentence embedding models, they could recover 50 to 70% of the input words just from the vectors themselves. There was another paper to pour more gas on the fire that was released this year. The authors are anonymous, but this paper, text embeddings reveal almost as much as text. They claim that if they constrain the input to 32 tokens or 32 words, that they could recover 90% of those 32 token inputs exactly from the embeddings, 92% of them. So that included extracting names and diagnoses from healthcare data. So 92% is a pretty big number that I think warrants some attention. We found another paper that was published this year that actually included open source software that you could run to experiment with these embedding inversion attacks. And so the premise of this is that if you've got a model that's been trained and you have access to provide some data to that model and get the embeddings that it spits out, you can take another model and train it to reverse the embeddings back to the inputs. So it's just the same thing. You just train a different model to invert the embedding. And so we took a pre-trained embedding model, picked a training data set, and we actually did this. And we were surprised at how well it could recover inputs. They in the paper they had that eye chart up there that I had up there about their results. And let's kind of look at a couple of them specifically so you don't have to squint quite as hard. They had 5 different sentence embedding models. They trained 4 different attackers, and the 2 best attackers that they had, these nucleus and beam ones, on 2 of the different embedding models. You can see they created the embeddings for this sentence: "I love playing the cello, it relaxes me." And they ran those embeddings through the attackers, and you can see the results. It didn't exactly match word for word the input, but if you read the question and you read what they spit out, you can see that it understood exactly what the sentence was about. So these inversion attacks are not the only potential attacks on the embeddings. I've got a coworker, Patrick Walsh. He's written a blog post about this, about the variety of attacks, and it's called "Embeddings Aren't Human Readable and Other Nonsense." And you can find that on Hacker Noon or on our website, Ironcore Labs. But I hope these will convince you that you need to handle vectors with care. Vectors are not the only thing, though. The OpenSearch vector database and most of the others allow you to store metadata along with the vectors. And, that metadata often is used to help filter queries. So maybe you only want to look at information about a particular user or company, maybe the age range or something. So the data in the metadata, the text in there or information in there, might be innocuous, but it could be very sensitive. And in particular, one way that if you're using these embeddings to provide context for a chatbot, you might be storing the text that produced the embedding as metadata so that you don't have to recreate it to feed the context back in. So you don't even need the inversion attack. If somebody gets into your data store, all the text is right there. So the metadata is important too. Those 2 things together are sensitive data that your security people are going to want you to pay attention to. So we've talked about what can go wrong. So let's talk about what we can do to help mitigate that. If you think about a typical flow where you've got inputs, you've got a model trained up, you're getting inputs, you're feeding them to it, it's spitting out embeddings, and you're stuffing them into a vector database. We could spend a whole other talk talking about securing the model and protecting it, but I want to focus on the embeddings and protecting them. The common way that you're going to protect sensitive data is to encrypt it, right? And that immediately begs the question, once you encrypt it, you can't do anything with it, right? You can't do vector searches over encrypted data. It's going to be meaningless if you don't have the key to decrypt it first. That's usually true, but there are a class of algorithms that are typically called property preserving, sometimes called data in use encryption algorithms, that can help with that problem. You can encrypt the data and still use it without decrypting it. So data in use just means it stays encrypted even in memory. And so it can be processed on a computer that isn't trusted. The computer doesn't have to have the key to unlock the data. It just handles it like it was normal data. Property preserving means that there's some property of the data that is still there even after it's encrypted, and you use that property to process the data. So this data is still meaningless without the decryption key, but you can still do certain types of operations on it. And so for a simple example, consider if you encrypt data normally, like just encrypt a string with AES, say, it's a probabilistic encryption. So even if you encrypted the same string 10 times with the same key, you're going to get 10 different results out. But you have the option, if you want to decrease the security a little bit, to get the same result out each time you use the same key. It's still encrypted. You still need the key to get back the original text that produced it. But if you use the same key, you can find out at least that that string is in your database. So maybe it's an email and you want to find all of the records that have this email address in it. You can encrypt the target email address that you're looking for. You can look through the database, find exact matches for it, even without being able to look at them and know what the email address was. So this is deterministic encryption. It's a form of property preserving encryption, and the property that's preserved is equality. So you can secure your data and still use it. And we use this in our cloaked search product to allow you to be able to search through a keyword index without being able to see what the keywords actually are. I'm going to tell you about how we can do that with a vector database too. And I think that's important because 40% of attacks in the wild are due to misconfiguration that exposes data or to stolen admin credentials. So it is important to make sure that the data that's sitting around out there isn't easily discernible. So how does this work in practice? We've got a way that you can take the embedding and its metadata and a key, pass those to an encrypt function. It gives you back an encrypted embedding, encrypted metadata. And so that data is essentially meaningless. If somebody hacked it, you wouldn't have to file a breach disclosure notification if the data got stolen, as long as you didn't tape the key to the data. That's always the important thing. Don't sit the key to your lockbox on top of the box. We talked a little bit about probabilistic versus deterministic encryption. The vectors are encrypted probabilistically, which means that every time you encrypt them, they would look different, but they're similar still. They're still neighbors in this vector space. And so the property that we preserve is distance in the like Euclidean or cosine similarity or dot product sense. So we might tweak each of the elements in the vector, but overall the distance between two vectors remains the same even after they're encrypted. Just like with deterministic encryption, that means there is some information that can be gleaned from looking at the encrypted data, but a lot less than looking at the unencrypted data. So because we preserve the distance, the standard distance metrics like cosine similarity or Euclidean distance continue to work, and you can continue to do nearest neighbor searches as long as you encrypt the query the same way before you send it to the database. So if you don't have the right key, you're not going to get meaningful data out. You can't do the nearest neighbor searches and get anything that means anything. And most importantly, if the data gets leaked, it's not a breach. So we've got a product called Cloaked AI that allows you to do this. You can use it as a proxy or as an SDK. Either way, when your application is ready to save data to the database, it produces one of these vectors. It just calls Cloaked AI to encrypt it. It manages a key for you. You encrypt it before you store it. We've got a lot of tools to help you with all of the pieces of encryption that suck and that are easy to screw up or to not pay enough attention to, like key management, key rotation, audit trails, permissions. So we've got tools that integrate with Cloaked AI to make that easier for you, and we optimized it to be pretty fast. So on the query side, you do the same thing. You encrypt the query, turn it into an embedding, give it to Cloaked AI, get back the encrypted one, and then you send that query to your vector database. The vector database doesn't need to know anything about the fact that there's encryption involved. It just does its job. And Cloaked AI is going to have negligible impact when you're comparing it to like some network calls out to your vector database. You get the query results back. Depending on what you're doing with them, you can ask Cloaked AI to decrypt them if you need the embedding, or decrypt the metadata that was encrypted along with it. In the process, the admins and the service don't learn anything about what the data is, what the queries were, but they can still do their job. So this can be deployed as a proxy, and we provide a simple SDK that you can use to talk to the proxy. And for some languages like Rust, you can actually get an in-process library so that you can put it directly into your application. So your app is getting data in, it's sends it to the model, gets the embedding back, calls cloaked AI to encrypt it, and then calls the vector database. So you just add that one call in there into the workflow to do the encryption. We get this question a lot, like, well, I turned on encryption at rest. I turned on disk encryption. Do I really need to do anything else? Yes, you do need to do something else. Encryption at rest is great if you're worried about forklift attacks, somebody breaking into your data center and carrying off a rack of hard drives, or if you're worried about somebody forgetting to wipe the hard drive when the controller goes out before they throw it in the garbage. But if it's on a machine that's running, the machine has the key, it's unlocked the data, it's essentially not encrypted at that point. So application layer encryption protects the data all the way through the process. So to summarize, this system is simple to implement. It really increases the security and privacy of the data. It allows you to make more choices about platforms and how you want to architect your solution so that the data is secure, but you can still do your core job. These AI embeddings are useful for a lot of different purposes: facial recognition, semantic search, stopping hallucinations. But they do, like human memories, they capture the essence of the inputs. And so you need to consider them as sensitive as the inputs were. And that makes them a new target for attackers. We talked about embedding inversion attacks and how it's not that difficult for you to leak data. Regulation is coming. I imagine that at least some of you have seen talks in Senate hearings about AI and privacy and stuff. I mean, this is a hot topic now. It's a lot of media attention. Right now, it's mostly focused on protecting models and talking about training data and how that might be leaked from the models. But the discussion is going to shift, I think, to privacy of the embeddings in pretty short order. So that's going to be the new frontier for privacy. We've got something that helps you get out in front of that and protect the AI memory right up front. So it will help you meet that requirement to be secure by design and by default. With that, I've used up most of my time, so I want to thank you for coming and listening. Stop by the booth. We do have donuts. We'll have candy in the afternoon, and we've got cool products that we want to talk to you about.